Okay. So sorry about that. A couple of things went wrong. And because of that, the audio might not be right. So if I'm really, really quiet or staticky, let me know. Okay, I think I'm a little bit staticky, but I might just have to deal with that. All right. Um, so um, this is just going to be like it normally is. I want to go through the entire practice test, kind of step by step, maybe give you some things that I would expect you to know. And then we'll just kind of like as you have questions, you can ask either in the chat, you can email me too. Uh, do we have a test tomorrow? No, Nico, you do not have a test. This is just for the honors guys. This is for all of Trig. So at some point you will take this. So if you want to watch, you can. But for you right now, no, you do not have to. Okay. Um, so just going from one all the way until the end. That the first couple shouldn't take very long. And then once we get into kind of deeper questions, um, we'll take our time. But first of all, actually, I need to grab my calculator. Okay. So find a positive and negative coterminal angle for each given angle. Okay, so coterminal angle, if you remember, that's angles that share the same terminal side and initial side, right? So the initial side is the same, and then it shares the same terminal side, but it is one rotation past that initial like angle, right? So it's either 360 degrees past it, before it, or any multiple of that. And then the same with 2 pi, right? So it's 2 pi past the actual angle. So this is easy. All right, so we just add 360 or subtract. None of these angles go to 900, so we can subtract. All right, so 255 is one of the angles. And the only option here is B, right? None of these other options have 255 a part of it. We can also check by subtracting 360 again, and we get negative 105. Right, so it has to be option B. Okay. Same thing for 7 pi over 4. We need to add 2 pi or subtract 2 pi. All right, so if we add 2 pi, we have to add fractions. We need a common denominator, so this is really 7 pi over 4 plus 8 pi over 4. Right, this is the same as 2 pi over 4, or sorry, 2 pi. Right, so 7 pi plus 8 pi, that's 15 pi over 4. And again, kind of the only option here is C. We could also subtract 8 pi over 4, so 7 pi over 4 minus 8 pi over 4 is equal to negative pi over 4. So that's a good check. Right, so it has to be option C. Easy enough. Again, coterminal is just one rotation past or one rotation before the given angle, or multiples, but I'm not really worried about that, right? So I could add like 16 pi to this and it'd be the same thing, but that's well past what I want. So just adding 360 or subtracting 360. Converting each degree measure into radians and each radian measure into degrees. And this is one-sided direction for these three. That's okay though. This is stoichiometry in really general terms, right? We're converting a unit to another unit, and we need a conversion factor, right? So every pi radians, that's equal to 180 degrees, right? So when we multiply by this, that's really just multiplying by 1. Same thing with 180 over pi. right? This is the same thing as 1. I know it doesn't look like that, but they're different units, right? So this is pi rads, right? That's technically the unit that goes with that. Right, so pi radians over on 180 degrees, that's equal to 1. Same thing for 180 over pi, right? So if we have negative 16 pi over 3, we need to multiply this by 180 over pi. These pi's cancel. Then we have negative 16 times 180 over 3. And then all we're really doing is simplifying. So negative 16 times 180 is equal to negative 2880. Divide that by 3. We get 960. So D is our answer. Okay, number 4, find the radian measure of the central angle of a circle of radius 12 that intercepts an arc length of 120 feet. Okay, so I like to kind of write what we have and what we don't. We need the radian measure of a central angle, right? So that's theta. We have radius, which is equal to 4. And we have an arc length of 120. Right, so arc length is always S. So we have S, we have R, and we need a theta. So we plug this into our equation, right? S is equal to R theta. And all we're doing is solving for theta. So we just got to do a little bit of algebra. Okay, so 120 is equal to 4 theta. So theta is equal to 120 divided by 4, which is, oh, my bad, I did this wrong. S is correct, R was 12 though, so gotta backtrack just a little bit. So S would be equal to 10 theta, and that makes more sense. Right, so if we divide both sides by 10, we get 12 is equal to theta. Sorry, yeah, 12. No? What did I just do wrong? Yeah, because I wrote our radius wrong again. It should be equal to 12. So this is equal to 10, and that's theta. Okay, I probably just confused some people. I just wrote down the radius incorrectly, right? So we still just plug these two numbers into our equation and solve for theta. Okay, that's all I did. So our correct answer here is B. I can go back to that. I hope I didn't confuse people too much with that. I just wrote some things wrong. Okay. Number 5, find the area of the sector of the circle with radius 4.3 and central angle 3/4 pi. So again, if we just write down what we have. And we should know that area is 1/2 r squared theta. So we just plug that in, right? So 1/2 4.3 squared times 3 pi over 4. We plug all that into a calculator, and we get an answer. Okay, so 0.5 times 4.3 squared times 3 pi divided by 4. So we get 21.8. That's our answer. Okay, so that the page should be it shouldn't take too long, and it should be decently easy. right? There's two equations we need to know. We need to know a conversion unit, and then we need to know what a coterminal angle is. So that shouldn't be too bad. Moving on to the next page, and I'm going to clean up some stuff here. Okay. So these next two require you to memorize that first quadrant of the unit circle. All right. And also kind of understanding what angle is what. So it's doing two things at once. All right. So the first thing we need to do is we need to understand what angle. That doesn't show up very well. What angle we're actually dealing with. So we need this angle theta on both of these. All right. So if we just think about this a little bit, we know that one full rotation is 360, right? So this goes in the opposite direction, 315. Okay. What would be the angle theta that would make that 360? That's our goal, right? So really we're taking 360 minus 315 and finding that, right? So that should be 45 degrees. That's the first thing. All right. Then we have to actually find the cosecant of that, right? And cosecant of theta, we should know is the same thing as 1 over the sine of theta, right? So that's what we're doing, right? So we need to find 1 over sine of 45. And you should notice that these aren't in decimal form, right? There's radicals and like whole numbers. So you could plug this into a calculator, get an answer, but it's not going to be obvious as to which one that is. Now you could plug in all of these and try and get an answer, which is fine. It's kind of cheating the system, but that's all right. What you should know, though, is that sine of 45, if you go to your unit circle, gives you the y-coordinate at 45 degrees, which is rad 2 over 2. So cosecant of theta is going to be 1 over rad 2 over 2. And then we need to rationalize that. So that's really equal to 2 over rad 2 multiplied by rad 2 over 2. So we get 2 rad 2 over 2, so we just get rad 2. So our answer is B. Okay, and I wrote that really fast, so I want to kind of give people to look at that. I'm going to explain that one more time, though, right? So 1 over, and then sine of 45 degrees, that's equal to rad 2 over 2. That's the y-coordinate at 45 degrees. Right, so that's how we get that fraction. 1 over rad 2 over 2 is just rad 2 over 2. And then in order to rationalize that, in order to get the square roots out of the denominator, we need to multiply by some clever form of 1. And when we do that and simplify, we just get rad 2. All right. So we need to do the same thing on the next one. I'm going to use a different color so it's obvious. All right. So we need to figure out what this angle theta is. So we go 1 full rotation. That's 360. And then the second full rotation would give us negative 720. But we only get negative 660 out of the way. Right, so again, 2 full rotations would give us 720, but we're only at 660. Right, so 720 minus 660. So we're dealing with 60 degrees, right? 60 more degrees would make this 2 full rotations. And then we need to do the same thing we did on the other one, right? So we need sine of 60 degrees. Okay, and this is where you would need to remember that first quadrant of the unit circle, right? 60 degrees gets you this point. Sine of 60 degrees gives you the y coordinate, right? So you have some x coordinate, y coordinate. Sine of that angle gives the y coordinate, right? So sine of 60, if you go to your unit circle, gives you rad 3 over 2. Okay, and if you need to look at that, if you go to our topics page, and then you go to chapter 4 material, I'll pull it up here in a second, just gotta find it. So topics, chapter 4 material, and then unit circle. Right, so again, we have sine of 60, so we go to 60 degrees. I don't know that you can see my mouse, but it's 60 degrees and then pi over 3. We're looking for that y coordinate. Okay, and that's all we're doing. Okay, so our answer here is part A, or answer A. Okay, so that's those two. Find the measure of each side indicated. This is going to be a little bit of calculator work. All right, so we have an angle theta. Right, theta is 60.3 degrees, and we have x, which is the adjacent side, and we have 2, which is the opposite side. Okay, so we need a function with adjacent and opposite, and a theta, and one that would do that is tangent. So we have tangent of 60.3 degrees is equal to 2 over x. Okay, and I actually think if this were on the ACT, they would actually leave it like this, so they wouldn't give you decimal answers. They would just be asking you to solve for x, right? So in order to solve for x, you'd multiply by x on both sides. And you don't need to do this for the test tomorrow, but it's good to know, right? So we'd get x times tangent of 60.3 is equal to 2. Divide by that tangent of 60. So x will be equal to that number, right? And if we plug that into our calculator, making sure that we're in degrees, right? And that's at mode. We want 2 divided by tangent of 60.3, and we get 1.14. Okay, so the closest answer there is B. Do we have to memorize the unit circle? You don't need to memorize the entire unit circle. You do need to memorize that first quadrant. All right, so from angle 0 degrees all the way up to 90. You need to memorize that stuff in between. And really 45 shouldn't be very difficult because you know those things are the same. And then the others are just flip-flops of one another. At what level of PEMDAS do trig functions fall? That's a good question. So it is a function, right? So this is pointing to some number, so a ratio of 2 numbers, right? So it's not like 60.3 means almost nothing in terms of algebra here, right? This is pointing to some degree measure on the unit circle, and it's pointing to, right, the ratio of these 2 points. Okay, it has almost nothing to do with like any algebra whatsoever, right? It is a function that points to 2 different things, right? So in terms of like order of operations, think of tangent of 60.3 or any trig function of any number is like, again, it's pointing to a different thing, right? So that all that in yellow, that's a certain number, right? So we wouldn't be able to divide out 60.3 or multiply by 60.3. You could, but it wouldn't do anything in terms of solving for x. I hope that makes sense. It's not like a parentheses or anything like that. It's an entire function, right? It'd be like saying x equals 4 over f of x, right? In order to solve for f of x, you need to get f of x by itself, and you would eventually get 4 divided by x, right? So that is the function. Okay. And again, good question. I hope that makes sense. On to the next one. Again, we have an angle theta, and we have the adjacent side. Right, so the adjacent side is equal to 7.9. The opposite side is 15. And this time we're trying to solve for theta. So we need a trig function with adjacent and opposite. So again, tangent and theta, right? So tangent of theta, tangent of our angle, is equal to 15 divided by 7.9. Right, and this is one of the last things we did, and it's been a while since we've actually like really done this. All right, so in order to undo a tangent, we need to take the inverse tangent, or arctan as some people call it, of both sides, right? So this is really what's happening. You don't need to know this, where you don't need to show this step. It's good to know that this is what's happening though. Okay, on the left-hand side, these 2 tangents, the tangent inverse and the tangent, just kind of cancel one another out. And then you have inverse tangent of 15 over 7.9. I think that's Betcher. Thank you, Betcher. All right. And that doesn't look like any of our answers. That would be something that would show up on the ACT though. Solve for theta. This would be an option. Okay, but we have a bunch of decimals here. So in order to do this on a graphing calculator, you would hit second tangent, and then you would plug in 15 divided by 7.9, and we'd get 62.23. So 62.2. So C is our answer. Okay, so we're typing it in exactly as is. In order to get this tangent inverse, you hit second, and then you hit tangent. And it'll give you that inverse tangent. Okay, and then same thing for number 10. This one's a little bit different, though, because it's all in like rationalized radians, right? So secant of theta, we have the opposite side, we have the hypotenuse. So opposite is 3 rad 15. Hypotenuse is 16. And secant, though, so secant of theta, can write that as 1 over cosine. But you can also write that as hypotenuse over adjacent. Why do we do inverse tangent as opposed to regular tangent? So the reason we do that is because we're trying to solve for just theta. So in order to get theta by itself, so just theta, we have to do the inverse tangent. So we have to cancel out. Right, so we have tangent of theta equals 15 divided by 7.9. We want just theta by itself. In order to do that, you have to do the inverse tangent of both sides, which just leaves you with theta is equal to the inverse tangent of 15 divided by 7.9. Okay, so I'll come back to that here in a second. I do want to finish number 10. So again, secant is hypotenuse over opposite. Adjacent. Yes. So we need the adjacent side. So the first thing we need to do is we need to find this side right here. So we need to use a little bit of Pythag. All right, so 16 squared should be equal to 3 rad 15 squared plus x squared. (16 squared is 256). 3 rad 15 squared is 9 times 15, which is 135. If we get x squared by itself, we get 121 is equal to x squared. So x is equal to 11. So that's our adjacent side. Right. So I'm going to finish number 10 real quick, and then I'll answer that. So this is the adjacent side. And then all we're doing is plugging that into our function, right? So secant of theta is hypotenuse over adjacent. So that'll be 16 divided by 11, which is B. Okay, so a couple questions on number 9. When solving for just theta and using the inverse, it applies to sine and cosine too. Yeah. So if we had, right, sine, this is just totally made up. So if we had sine of theta is equal to, let's say, 7 over 15. Again, made up. It has nothing to do with what's above it. All right, so don't worry about that. Right? In order to solve for theta, we would take the inverse sine of both sides. So we get theta is equal to sine inverse, or arc sine, of 7 over 15. And then whatever that number is, that'd be our angle. And then same thing for cosine. It's a little bit trickier with secant and cosecant, because you'd have to do 1 over the inverse, but I'm probably not going to make you do that tomorrow. Okay, so that was page 2, and I think that's it for multiple choice. All right, so I'll scroll through this later, but I want to get to the kind of the harder stuff. Not harder stuff, just longer stuff maybe. Move these down. One day I'm gonna do this beforehand, but not today. All right. So using radians, find the amplitude and period of each function, then graph the function, label all points, all the critical points, and then show all work for credit. All right. Bottom line is be able to graph it as we did in class. So there's a couple of things that we need to do like before any actual graphing, and that's to label a couple of things, right? So the easiest thing to get is the amplitude. That's always the thing in front of sine attached to it, right? So that's 1/2. And that's how far it goes up or down from our center line, which is always going to be this thing kind of trailing everything, or in front of, right? But it's the constant that's not attached to sine, right? So our shift is equal to -2, right? So our center line is -2. It'll go up 1/2 and also down 1/2. All right, so if we want to draw that, kind of as we go. This center line is -2. It will go up to -2.5. Not -2.5, -1.5. And then down to -2.5. Right, so that's the skeleton of our function so far. Okay, 2 easy things to do, really easy points to get. Right, then we need to find the period. All right, so the period is always going to be 2 pi over b, and b is always the thing attached to theta. Right, so 2 pi over 4, which is just pi over 2. Okay, that tells us how long it takes to do one full cycle of the graph. Right, so whenever it starts to repeat, that's 1 period. All right, so it goes beyond that, but this little section right here, that's 1 period. All right, then we need to find a good start point and a good end point. The start is when all of this in parentheses is equal to 0. Right, because that's when the sine function starts, right? That's when our unit circle starts at 0 degrees and 0 radians. All right, so if we solve for this, we get -pi/16. And we also need to get an endpoint, which you can do in 2 different ways. I always find it this way, by setting 4 theta plus pi over 4 equal to 2 pi, right? Because that's 1 full rotation of a circle. All right, so when we solve this, 2 pi minus pi over 4 is 7 pi over 4. And then divide by 4 on both sides, we get 7 pi over 16. All right, so endpoint, start point. And then the distance between those 2 things is pi over 2. Okay, then we can actually like start graphing it and labeling some points, right? So sine starts in the middle, goes up to a maximum, comes back down to a minimum, and then comes back up. Okay, so that is the sine graph. It keeps going, but we're just worried about the period that I have drawn. All right, so the start point, that point right there, is -2. Sorry, not -2. It's -pi/16 comma -2. All right, so that's the start point. Our end point over here is 7 pi/16 comma -2. Okay, and our job is to find our critical points, right? So our maximum and our minimum, and also the 0 between. Right, and each of those points are exactly 1/4 of the period after the last. Right, so a good way to do this is to go like halfway between, right? So to find this middle point, -pi/16 to 7 pi/6, that's our period, right? So that's 8 pi/16. But we need to divide that by 2, right? So that's 4 pi/16. right? So if we add this to our start point, we get our middle point. So this is 3 pi over 16, comma negative 2. Right, so again, this is our period. This is half of our period, which is the point in the middle. And then maybe I'll do this next part in like a darker green. Half of that is 2 pi over 16. Right, so that would give us this point. All right, so negative pi over 16 plus 2 pi over 16, that just gives us pi over 16, comma negative 1.5. And then we have to do that down here too, right? So 3 pi over 16 plus 2 pi over 16, that gives us 5 pi over 16, comma negative 2.5. All right, so I want to give people like a second to kind of digest this. And as that's happening, please ask any questions that you have, because this is a lot and it's kind of putting a lot together. But again, please ask if you have questions. Daniel Evans, you absolutely have a test tomorrow. Okay. So again, if you have questions over this, I can always go back to it, but I do want to do the next part, which is just graphing the inverse. Okay, and the inverse is actually really easy, right? So from question 11, graph the inverse of the function. Okay, so that was sine. So we want to graph cosecant, right? So we're graphing 1/2 the cosecant of 4 theta plus pi over 4 minus 2. Well, we only have to graph sine, cosine, and tangent. I'm hoping this answers your question. No, you're going to have to graph sine, cosine, and its inverse, and then you have to graph a tangent. Okay, cotangent is basically the same thing as tangent. It's just shifted, which is why I'm not super interested in it. But the difference between sine and cosine, and then cosecant and secant, that is kind of important. All right, so when we do this, I'm just going to copy all this. That's pretty much going to give us our answer. Oops. Right, so this gives us our answer pretty much. Except I'm going to clear some of these points. All right, so everywhere whenever we're graphing an inverse, um, every time our graph hits the x-axis, that is going to be an asymptote. Right, and there's a reason behind that, and I'll tell you that here in a second. But the gist here is that everywhere we have a 0, we have an asymptote. Right, and these asymptotes are exactly where they were before. Right, so this is x, I guess if you want to call it theta, but we can just call it x for now, is equal to negative pi over 16. Right, that's the vertical line at negative pi over 16. This will be at 3 pi over 16. And then this asymptote will be 7 pi over 16. Right, and that's directly from what I had above. So like all the work that we've done is, all the work that we did up top is, it does this for us. Okay. So those are the asymptotes. And then our actual graph is no longer, right, this, which I'll make dotted. It is the inverse, right? So from our max, I'll do it in a different color. From our max, we go up toward the asymptotes. And from our minimum, we go down toward our asymptotes. And that would repeat, but I'm really only worried about the first two that I drew. And again, 2 good points to label are these guys, which we had before and I deleted. This is 5 pi over 16, comma negative 2.5. And then this is pi over 16, comma negative 1.5. So again, like all the work that you did before, it does all of this for us. We just got to draw a different part of it, right? And our graph isn't anything in blue. It's all this stuff in green. So again, I'll give people kind of a second to look at this and ask any questions that they have, but this is how we graph any inverse, right? Wherever our original graph crosses our center line, that's where we have an asymptote. And then we're drawing up from the maximums and down from the minimums. Okay. So next is tangent, right? So there will be a tangent graph. Tangent isn't that bad to deal with. Remember that tangent of any angle is also sine over cosine. And for our sake, we just have to worry about the denominator here, right? So there kind of is an amplitude. That's still 1/2. But I'm more worried about this bottom, this denominator, and the theta over 3. Okay. So when we have tangent of theta over 3, I can really rewrite that as sine of theta over 3 over cosine of theta over 3. Okay. So whenever we're dealing with any variable in the denominator, we have to see when that denominator is equal to 0 for a vertical asymptote, right? So for this graph, which we can kind of start to draw, for our graph, what the really determining factor here is where the asymptotes are. That tells us almost everything we need to know, right? And that happens when this guy is equal to 0. Right, and cosine is equal to 0 when the inside, right, so cosine, again, think of the unit circle. Cosine is the x value. That's going to be equal to 0 at the top and at the bottom. Right, so pi over 2 and 3 pi over 2. And then any multiple, okay? So we need when theta over 3 is equal to pi over 2. So theta is equal to 3 pi over 2. And, right, so we're going to find two of them. Theta is equal to 3 pi over 2. So theta is equal to 3 pi. Nope, 9 pi over 2. Right, so we can graph that. It's easiest to think about this as like the center, right? So our first asymptote be right about here, right? So this is theta is equal to 3 pi over 2. Yep, that's it. And then there's going to be one over here where theta is equal to 9 pi over 2. And then the tangent function, all that is kind of an S curve, an S-like curve, through the middle and up toward the asymptotes, right? So we have the two asymptotes, and then we just need this point. This point is halfway between, and this is 0 because there's no shift, right? So halfway between 3 pi over 2 and 9 pi over 2 is 6 pi over 2. So that point is 6 pi over 2 comma 0. Well, so I thought we only needed to graph one period for the tangent, so you only need one asymptote. You really do need two, because you need, right, I guess well, yeah, you need two asymptotes. Because this is, right, the actual period of tangent is negative pi over 2 to pi over 2. And if you're confused about this, don't worry. So we need where it goes down to and where it goes up to. Right, so we need this left asymptote and this right asymptote. That also tells us where our 0 is. Right, halfway between those two things tells us where that is. There's other ways to do that, but that's probably easier. You are right, right? We only need to graph one period, but we need two asymptotes to do that. Okay, so again, I'll let people kind of look at this and digest it. And as you have questions, please ask. So we don't need to worry about start and end points, just the asymptotes. Yeah. I would think of this at like these two asymptotes as a start and end point, but they're asymptotes, so it's kind of a soft start and a soft end point. There's no real start and end to them because they go down to infinity. Right? Think of it like an open interval. Right? These asymptotes are not inclusive. So yes. Two asymptotes, everything in between. That's what I'm worried about. Okay, we got a couple more. So last page. Number 14, we got to know those identities, right? So we got to know the ratio, the ratio identities, I think is what you call them, the Pythagorean identities, and then the inverse identities, right? And that'll help you get number 14, right? So number 14 for this, what I would do is multiply these two things. So we can FOIL, right? So 1 times 1, that's 1. 1 times sine, 1 times negative sine. It's negative sine. Sine times 1, that's plus sine. Is there only going to be one trig identity problem on the test? Yes. And then minus sine squared. And that should be equal to cosine squared. All right. Negative sine and positive sine, those cancel. So we're left with 1 minus sine squared. All right, and we should recognize 1 minus sine squared, right? So actually, like the founding Pythagorean identity says that sine squared plus cosine squared is always equal to 1. All right, so if we subtract sine over, we get 1 minus sine squared, and that's equal to cosine squared. Right, so this is just equal to cosine squared. And then we're done. Okay, so the last one, I did go over in class, so I'm hoping people remember that. I'll go over it again. But the two things we need to know are, right, like linear speed. Like, again, if you were twirling something around and you let it go, like what speed would it be going at? That is equal to S, our arc length, over time. Which, if you remember our equation for arc length, it's the same thing as r theta over time. And then angular speed, which is like how many radians a second or minute are you traveling, right? So if you're twirling something around, basically what angle are you covering in what time? So that's just going to be theta over time. And fun fact, from that we could write V is equal to R times W. You don't need to know that. I just noticed that. All right, so a 2-inch diameter pulley on an electric motor that runs at 1,700 revolutions per minute is connected by a belt to a 4-inch diameter pulley on a saw arbor. Find the angular speed of each pulley. Right, so we have 2-inch diameter pulley. Connected to a 4-inch diameter pulley. Diameter, so this should be 2. And this should be 1. And then these two are connected. There's like a band that goes from both of them. That's drawing, it's spinning the blade, right? So on this red one, we need W, right? And that is going 1,700 revolutions a minute, right? So that's 1,700 times 2 pi per minute. Which is 3,400 pi radians per minute. So that's the easy part. This goes to a belt, which has some speed. Which is going to be r, our radius, times our angle theta, which is 3,400 pi per minute. So we just get 3,400 pi. So that's not what we're actually trying to find, but we need to convert this into the angular speed here. And again, some of you guys know how to do this a whole lot easier. I have to write this out. I'm not sure why. But then we have an angle. And now we have a radius. So then that would convert it to the speed of this, right? Right, if it's going this direction. Which will be equal to radius times our angle theta over time, and we can solve for theta, right? So if we just divide by 2, theta is 1,700 pi. And this would be per minute, right? So then this and this are our answers. And then find the revolutions per minute of the saw, right? So if we're going 1,700 pi a minute, we would just divide that by 2. We'd get 850. So 850 rotations a minute. So again, kind of a lot of stuff. So I'll give people a second to look at this. And as you have questions, go ahead and ask them. .850 pi or just 850? Well, because I wrote this wrong. 1 revolution is 2 pi radians, so this really should be 2 pi. So then, right, these pi's would cancel. So it's just 850. Okay, so that is the entire test. I'm hoping that you've seen everything. Just in case you don't, I'm gonna scroll up through the other part of the test, right? So I'm just going to kind of take my time scrolling up through it. Uh, and if no one has questions by the end, I'll end it. But I will try my best to answer questions as people have them. So that's all the work that there is. But I will gladly ask questions over different problems if you have them. All right, so I'm going to mute myself and I'll just kind of slowly scroll up. Okay, number 13. So for tangent, you should remember from our identities that we can rewrite tangent as sine over cosine, right? Um, Everything else is still the same, right? So 1/2 is still kind of our amplitude. It just means less. It's kind of how steep this gets, and how fast it gets, right? So that doesn't mean a whole lot for us. This 0, I wrote that in. That's just the shift, right? So our center line is 0. So two things, just get those out of the way real quick. And then we can rewrite tangent of theta over 3. So I have it written here. I'm just going to write it again. So tangent of theta over 3, we can rewrite as sine of theta over 3 over cosine of theta over 3. All right. Now, whenever you have a fraction and you have a variable in the denominator, you got to check to see when that's equal to 0. Right? So we just take this cosine of theta and set it equal to 0. Okay. Cosine is only ever going to be equal to 0 when we have angles of pi over 2 and 3 pi over 2. Right? Because cosine gives us the x value on the unit circle, right? So this is only true when our angle is equal to pi over 2 or 3 pi over 2. Solve for theta. We get theta is equal to 3 pi over 2 or theta is equal to 9 pi over 2. Okay, those are our angles which would cause us to have an asymptote, right? That's when the denominator is equal to 0, so we have some undefined behavior there. So that's where these come in. So those are our asymptotes, and then we just draw the S curve down to the left, up to the right, and then we find the center point. Right, so halfway between 3 pi over 2 and 9 pi over 2, that gives us 6 pi over 2. And then we don't have a shift, so our our y coordinate is 0. I hope that clears it up. All right, I'm going to continue to scroll up. If you still have questions over it, again, don't be afraid to ask. Since doesn't seem like there are any other questions, um, I'm gonna call this in the next like minute or so. If you have questions, feel free to email me. Feel free to come in. Like I'll be in my classroom at 7:30. So if you want to come in at like 8 or 8:30, that's fine. I don't have a first period, so I think so. Yeah, my first period I think is the 5th. Um, yeah. So I have a study hall period 5. So um, I'm not going to be in any other classroom. So I'll be in 317, right? So feel free to come in then. Feel free to ask questions like right before class. That's fine. I don't think this would take a full hour. So we can spend a couple minutes too before the test. All right. So again, if you have questions, let me know. Otherwise, I'm gonna close this up, and I will see you guys tomorrow. All right. Yes, this will be available to watch on playbacks, and actually, you can, if you just have this tab open, you can just kind of scroll through it. But all right, I'll see you guys tomorrow.